Start today. My question to you is, can you remember how to find the area of a trapezium and can you prove the formula? Have a go. I remember a few years ago, I thought the best way of proving the area of a trapezium was to call this one A and then split it into little parts, triangles and rectangles. This will also be A, and then if I call this X, this bit, if the bottom is B, would be B minus A minus X, and we could use compound area to work out the area, which turns out to be a half A plus B times H. So maybe you tried it that way, but it's just very technical and just unnecessarily algebraic, and you have to manipulate lots of things. There's actually an amazing way of doing it that I now want to discuss with you, and that is to use the idea of the area of a parallelogram. Now, the area of parallelogram is base times height, because you can imagine taking this bit, cutting it off and sticking it on there. It's the same as the area of a rectangle. So as long as you're happy with that basic proof, then we can go on to the area of a trapezium. And what we can do for any trapezium is, now the base is B and the height is A, sorry, the top length is A. What we can do is we can actually replicate the trapezium and draw it upside down next to the original one. Then this length is A and this length is B, and we're left with the area of the two of them is going to be A plus B times H. But we don't want two of them, so we just have to have it. I think that's an underrated proof in mathematics and geometry. You don't tend to see it. Maybe you have seen it before, maybe that's how you did it. But for me, that is a lovely proof that the area of the trapezium is a half times A plus B times H. All right, the next bit I want you to do is just, well, to be honest, if you can do that, this is just simple substitution, but make sure that you can find the area of trapezium by substituting in. I'll give you a moment. I'm going to we'll pause the video now. Okay, so the first one, you would have added 3 plus 7 to get 10, halved it to get 5, times that by 4 to get 20, substituting in. Similar here, you've just got to now realize that the trapezium is on its side and it's a right angle trapezium. That's absolutely fine. It still satisfies the conditions for a trapezium. By the way, a square satisfies the conditions for a trapezium. All squares are rectangles, which are parallelograms, which are trapeziums. They still satisfy the conditions, the formulae that work for them, which is pretty cool, I think. So anyway, in this case, we'd probably use A as 6 and B as 11. You can interchange them, actually. It doesn't matter. There's nothing special about A and B here. The height does have to be 4. So then you add them together, you're going to get 17. I'm not going to have that, but I'm going to have the height this time too. 17 times 2, 34. And then finally, this is actually the sort of trapezium we're going to be looking at today. And it's going to be half y0 plus y1 times h. And you'll see how that's going to come into it. But that's us using the general formula really, but realizing the trapezium again is on its side. So the question now is, what is the trapezium rule? And the answer is that basically we're going to estimate curves using straight lines, and that is, we're going to change them from being these nice smooth things to just things that are made up by straight lines, and the area underneath will then be trapezia. I think to start with, I'm just going to draw some. So I might draw like a trapezium like that, and then a little one like that. And you can see I can approximately, if I could work out the area of these trapeziums, I'm going to use the word trapezia from now on because that is the proper plural. Then I could estimate the area underneath. Now, why do that? Why not integrate it exactly? Well, two reasons really. Some functions you cannot integrate exactly. If I suddenly start writing down a random function like this, and then maybe I multiply it by e to the x, and then sine x to the 4, and then I put, I don't know, I divide all of that by ln x, and I integrate that with respect to x. And am I going to be able to do that exactly? And I don't know for sure, but my guess is no. And that there are certainly many functions out there that you cannot integrate exactly. Oh, I've got a really good one. It's not possible to integrate this exactly, and we're going to come back to this function in statistics actually. But you can do it numerically, and it's really important. This is a very important function. Also, one other reason, sometimes functions don't even have a nice form like this. I mean, you might not think this is nice, but it might just be that I can find it numerically, the function itself, but that's it. And I can find it wherever I want, but it doesn't actually have an analytic form such as this. And in that case, you're going to have to use numerical integration. You don't have anything to actually integrate exactly with. So we're going to approximate, we're going to work algebraically to start with to kind of get the formula that we need to be able to, the trapezium rule formula essentially. Now we're going to be integrating between A and B. Note, these are different than the A and B I had with the original formula for the trapezium that you learnt. A is now the starting point for my integration. It's not that top length on the base. So just be aware, and we're going to really stick with this one on the bottom right, y0, y1. We'll see what those are in a minute. Okay, second thing is that we're going to make it as simple as possible. So we're definitely not going to make the trapezium different sizes, because we'd actually have to work them all out separately then. We're going to come up with an algorithm essentially for how we could implement it, because at the end of the day, if you were doing this for a complicated function, you'd probably be using 100 trapezium, maybe even more. Depends on the length of your interval, and you don't want to be doing that by hand. You don't want to be trying to draw the function. You want an algorithm that will work. So that's what we're going to try and get. Okay, so the first thing is to work out, we're using 4 trapezia, so what's the height? And it is going to be the height, this length along here is going to be the height of each trapezium. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8 squares. So each trapezium is going to be 4 in height. Okay, and I can draw them all on like this. Did I say 4? Sorry, I don't know what I just said there, but I think there's going to be 2 squares in height. And how could we get it in general? Well, I'm going to call this little thing h, but they're all h. And it's going to be this length here, which is b minus a. And then I'm going to be dividing by the number of intervals I'm splitting it into. So in this case, 4. Okay, next point. So if I know my starting value, well, I'm actually going to call that x0. My next value is going to be x1, and that will simply be x0 plus h. So I can generate all of my x values by just adding h onto them. I'm going to call them x0, x1, x2, x3, and x4. That's the standard notation used. And then to go with that are going to be some values of y. So I'm going to draw these in blue, going along. I'm just reading off, like I'm just showing you on the graph here where they would be. Obviously, we would just substitute it into the function that we know, or we would know the function at that value, and then we're going to get corresponding y0, y1, y2, y3, and y4. Okay, brilliant. Now, if I want to work out the area of this trapezium, then it's got height of h, and then I'm going to add on the y0 and the y1, these lengths here. The next one is going to be here, this red one, and that's going to be the same height of h, but now it's going to be y1 plus y2. This one here, similar sort of thing, y2 plus y3, and then finally, I missed out the h there, didn't I? Sorry. and that should be a h. There should be a h here. y3 plus y4. All right. And then I can simplify it. I can notice that in each one, I've got a half h that I can factorize out. So I'm going to write a half h, and then I can just figure out what's left. So I'm going to get y0 plus y1 plus y1 plus y2 plus y2 plus y3 plus y3 plus y4. And that thing I've just written is exactly the same as this. I've just taken out a common factor of a half h. Why? Because this is a nice bit now. I can simplify it to y1 plus y0 plus 2 lots of y1 plus 2 lots of y2 plus 2 lots of y3 plus y4. And that is it. If I want to work out the area, approximate the area under the curve using trapezia, for 4 trapezia, then this is a formula that I could very quickly implement. I just need to remember I only include the endpoints once, because they're only, like the other points, are part of 2 trapezia. So that's why we get this double counting going on, whereas the one to do with A is just there once, as is the one to do with B. And to work out h, we've got this nice formula here. Of course, 4 trapezia is not going to be very accurate if your curve is all over the place. Like here, it would be okay, but we want to be able to make it better. And if my curve goes up and down like this, then 4 trapezia is going to be pretty rubbish. So how can we generalize this and not have a formula just for 4, but for n trapezia? Well, it's the same idea. And I'm just going to give you the overview of it. So now I've got some sort of trapezia here, and I don't know the width. Okay, I could make it as small as I want, and I've got lots of them. They're all going to have this height. I'm still calling it the height, even though it's now the base. It's like it's that length that is essentially the height of the trapezium. Okay, how could I work that out? Well, the full length is again going to be b minus a. But this time I'm splitting it up into these n intervals, these n trapezia. So it's exactly the same as before, but with 4 replaced by n. That's going to be really important. And then we're going to get our x0, x1, x2 again, all the way up to the last point, which is going to be xn. Instead of x4, we've got xn. And in the same way, I'm going to get y0, y1, all the way up to yn. And the area is going to work out in the same kind of way. The first one is going to be a half h y0 plus y1. That's this one in red. Second one is going to be a half h y1 plus y2. And then I'm going to go all the way up to this very last one. Sorry, it's just a rough little sketch of it here. And that, so then I can do plus dot 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 dot, carries on the same way, plus a half h y n minus 1. This point here is x n minus 1 plus y n. And hopefully you can see where we're going with this. We're going to factorize it out in exactly the same way. A half h y0 plus 2y1 plus 2y2 plus dot 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 plus there's going to be 2 lots of yn minus 1 because there would have been one with this trapezia as well corresponding with it, plus yn. So once we did the hard bit with the 4, we did that in quite some detail. This is the formula in general. So we can now say basically, right, I know my starting points, I know my end points, I know how many trapezia I want to use, so I can work out what h is. I can then use my starting point to get the value of the function. I can add on h to get the next x value. I can work out the value of the function. I can add on it h to get the next x value. I can find the value of the function and so on, and you can construct an algorithm to how to find a trapezium, the area of the trapezium. You can make a better estimate by using more trapezia. And then basically, like if you were doing this scientifically, you might run a computer program, double the number of trapezia, and if the answer doesn't change, you know that you've done it correctly. So if you're writing a computer program to do a long calculation, you'd run it, and then you'd run it again with all the trapezia kind of doubled, or you check each little subroutine to check that you're using enough trapezia, basically. Okay, this formula you don't have to learn. It is actually given in the formula book. In A level, you're not going to be asked to do 100 trapezia. You're just going to be asked, can you implement it? But obviously in maths, A level, it's really important to see where these things come from and be happy. And if I asked you to derive it, could you derive it? So actually, this is how it's written in the formula book. They group all of the ones that's multiplied by 2 together, and then they leave the two endpoints by themselves. Okay, there's nothing. No, it's exactly the same as what I've done, just a slight rearrangement, and they give you the h as well. So if we know b, a, and n, and we know the function, then we can implement the trapezium rule and find approximate areas. Okay, we've derived the trapezium rule for n trapezia, and now we're going to implement it on a function. I don't think it's possible to easily integrate this function. I'm not sure if we can do it at all. So we're going to have a go at doing it for 3 strips. That's exactly the same as saying 3 intervals or 3 trapezia. So I've got my function, not actually sure what it looks like, and I'm going to have 4 different x values, but these 3 trapezia that go with it. Okay, first thing to do, I think, is to write down our value of a, our value of b, and we get that from here, and then we can write down our value of h. It's going to be 3 minus 0 divided by the number of intervals, which is 3, so they're each going to be 1. Okay, so nice length in this case. All right, and then my recommendation is to draw a little table. So I've got x0, x1, because I'm just adding 1 to it, this value of h. This is how I get all my values. I just add h to it each time, x2 and x3. And then I'm going to work out y0, y1, y2, and y3 by substituting it into what we call the integrand. Okay. It's the square root of, actually, do you know what? Best thing to do here is just use the table function. This will speed it up, especially when you get more values. Not interested in the second function. Start at 0, end at 3, go up in ones, and we've got it. Now, we lose the exact values here. That's the only thing about using a table function. It's a bit frustrating because this is just root 2. So you'll get 1 and root 2. So in this case, although I've used a table function, I'm just going to use it to help me out a little bit. This one is 3. And actually, 5.29, when I substitute 3 in, I'm going to get 27. I'm going to get root 28. Now, if you don't leave it exact like this, then you have to write down enough decimal places. It doesn't say in the answer, but typically we give answers to 3 significant figures. So really, you should write down everything, all your non-exact answers down to 4. I'd say actually 5 significant figures. So just make sure you are not rounding too early because you'll lose accuracy. And then we're there. We just need to transform this formula into one that works for 3 intervals. So I think a good idea is to first of all write it down for the 3 intervals. A half h, then it's going to be y0. Remember, n is 3 here. Probably should have said that. N is 3, so we're going to add on y3, and then we're going to do 2 lots of y1 plus y2. Curly brackets are used just because we've got brackets inside brackets, and it distinguishes, it shows you that those two go together. Okay, I'm just going to move this down, bear with me. Didn't leave enough space, right. And then it's just a case of substituting in. A half times 1, so I can just ignore that actually. And then I've got y0 plus y3 plus 2 lots of this. Okay, and that is our area, but we're being asked to find it numerically, so I just need to substitute in. Just do it really carefully. Okay, sometimes you have to press right to get outside of the roots. And the last one is 3. I've got to close 2 brackets, and we get 7.55996. Which I'm going to round to 3 significant figures. Because I can't, I mean, sometimes you want to leave your, if you were doing this on a computer, you'd want to like compare your accuracy, but here I'm just recognizing that it's not exact, and I'm rounding it to 3 significant figures. Okay, what I'd like you to do is do exactly the same for 6 strips. Pause the video now and have a go. Set it up in the same kind of way that I've done. See if your answer is close to 7.56. It should be fairly close, hopefully. I'm just going to give a works, like the solution to this that I got from somewhere. So you would set up, you would get h equals 0.5 by now dividing through by 6. N is equal to 6. You would draw a little table like this. You can still get exact values, actually, but otherwise you're going to have to write enough decimal places. Here it is with 6 strips. So we got y0 plus y6, and then y1, y2, y3, y4, y5, and we get 7.39. So if you can do that, if you can do that example yourself, you can do the trapezium rule in general. Well done. The last little question was explain why the trapezium rule is an overestimate of the true value. This is a bit of a harsh question because they haven't given you the graph. So I'm just going to quickly talk about this idea now. I'm going to give you the graph. So why is it an overestimate? Well, it's because the trapezia all lie slightly above, like there's little bits of area that lie above the function. So you would say something like this from the graph of the function. Like I wouldn't expect you to draw the graph here. I'd expect you to be given it. It's clear the trapezia lie above the curve, so the trapezium rule gives an overestimate. So sometimes it will give an overestimate and sometimes it will give an underestimate. And essentially, if the curve is convex, that means it's sort of bending. What does that mean again? That means the second derivative is greater than 0 because the gradient is increasing. Then it will be an overestimate. And if the curve is concave, that's when the second derivative is less than 0. It's the gradient is decreasing. Then it will be an underestimate. Okay, so just be aware of these things. I don't know if you need to use the word convex and concave. You will have seen them already, but just be aware essentially that of overestimates and underestimates. And as I said before, the more strips or trapezia used, the more accuracy you're going to have, because essentially if I divided these into two, then suddenly like the little bit of area that is above is going to be less. Okay, brilliant. Alrighty, one bonus example. So if you're confident, you could skip this, but I think there's you could have a go at it as an extra question, and I'm going to talk about a nice result that comes from it at the end. All right, let's do this. So we've got 4 intervals. That means n is equal to 4, a is equal to 0, b is equal to 1. That means h is equal to 1 minus 0 over 4, and each trapezium is going to be 0.25 in width, let's say. Let's construct our table. X, Y. First one is going to be 0, then we add on h, then we add on h again and again and again. Work out the value of y's. I would use the table function now. I've done this already, so just substitute it in, and I get 4, 3.7647, 3.2, 2.56, and 2. Okay, I'm going to have lost some accuracy maybe with this one. Not sure, or maybe that is exact, not sure. Write down a trapezium rule for this 4 intervals. So this integral is going to be approximately equal to half h y0 plus y4 plus 2. Why did I do a curly bracket there? Sorry. Plus 2 lots of y1 plus y2 plus y3. Nice one. So that's going to equal a half times 0.25. If you're rushing in an exam, then I'd say, like, don't worry writing out this next bit, because it just takes a fair bit of time. 4 plus 2. I might just lose a minute that could be important somewhere else. I know I say as a teacher, like, always show where you're working. But we've got the table. Okay, 0.5 times 0.25 times 4 plus 2 plus 2 lots. Close the bracket again, and we get 3.131175. All right, what's the nice result, I hear you say? Well, you can actually do this integral exactly. This is what the graph looks like, and if you do the integral, exactly, you can actually do a substitution. X equals tan u, and that means u is equal to inverse tan of x. So when x is equal to 0, u is equal to 0, because inverse tan of 0 is 0. When x is equal to 1, inverse tan is actually pi over 4. This is going to become the integral then of pi over 4 between 0, 4 over 1 plus tan squared u. we still need to work out dx by du. Dx by du is equal to sec squared u. But actually, 1 plus tan squared u is equal to sec squared u. So these cancel out. That's an identity that you might be familiar with. And therefore, my answer is just going to be for u, when I integrate 4, evaluated between pi over 4 and 0. And I'm going to get 4 lots of pi over 4, or pi. So we can use numerical integration to make estimates. It's only 3.131175, and actually this is not going to give us a very good estimate. It doesn't scale well even with, as I increase the number of intervals. But I just wanted to kind of show that you can use numerical integration to make these estimates. I think that's really nice. Anyway, hopefully you're happy with that. Try some more. Make sure you've mastered trapezium rule. It's not a bad second year topic at all. Just make sure you've got the formula sorted and you know how to implement it. Thank you.